Hello everyone, welcome back. Today I want to talk about counting 101, some basic principles and concepts. The materials will be covered in Math 130, 255, 185. Let's start with some preliminaries. They look very simple, but kind of tricky. All right, so this is the first problem. How many numbers are there if you start to count from 3 to 103? Normally, I would get the answers like 100, or some people would say 101, and then 102. Actually, some people would say 102. To think about this problem, we can look at a similar problem. There are two ways of thinking, okay? One way is to think about how many numbers are there are if you start to count from 1 to 100. Almost everybody would say it's 100. Okay, 1 to 100, just count 1, 2, 3 to 100. So you have 100 of them. But then you notice that 100 minus 1 is actually 99. That's normally people to get 100 from here because 103 minus 3. But go back to 1 to 100. 100 minus 1 is 99. But there are 100 numbers. So you need to add 1. You need to add 1 back to 99 and still get 100. So a similar argument would be here. If you subtract 3 from 103, you get 100, but you need to add 1 back. So the right answer should be 101. Now, another way of thinking is that if you count from 1 to 103, and there are 103 numbers, that's no problem. Now, if you subtract 3 from 103, so it's like you are cutting 1, 2, 3 from 1, 2, 3 to 103. But this number 3 should be included when you count from 3 to 103. So that number should be added back. There's one number, right? It's not adding 3. So there's one number. So you add 1 back. So you would get 103 minus 3, and you're going to add 1 back. So again, it's 101. All right, so this kind of thinking, please keep in mind because we're going to use that for some formulas. All right, let's work with the variables. Let's say you count from k to k plus n. How many numbers are there? You're sort of doing, you have k, then you have k plus 1, then dot, 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 you have k plus n. Then how many numbers are there? By similar argument, we did that earlier, right? It should be k plus n minus k, but you need to add 1 back. So actually there are n plus 1 numbers. Right? From k to k plus n, there are n plus 1 numbers. Now let's think backwards. What I mean is that if you start to count from k, getting bigger and bigger, okay? Start from k, then you have k plus 1, and then dot, dot, dot. If I tell you there are n numbers here, what is the last number? What is the expression of the last number? Well, it's tempting to say k plus n, but then k plus n minus k, you need to add 1 back. Actually, you have n plus 1 numbers if the last expression is k plus n. So in fact, the last expression should be k plus n minus 1. All right, and then you do k plus n minus 1 minus k, then add 1 back, you have exactly n numbers. All right, so if you start from k and you have n numbers, the last term is actually k plus n minus 1. Now, what if we count downward from n, and there are k numbers? Okay, you start from n, then you have n minus 1, and dot, 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 and I tell you there are k numbers, okay? You're getting smaller, right? It's tempting to write n minus k, but then n minus k, you need to add 1 back, right? You would get k plus 1 numbers. So that's not what we had. We had actually k numbers. So last one should be n minus k plus 1. Okay? So now you have n minus k plus 1, you get exactly, plus 1 in the end. You would get exactly k numbers. All right, so something like n minus k plus 1, and then plus 1. That is k minus 1 plus 1, you get a k number. That's exactly what we wanted. Okay, and these formulas are will be used later on, so I hope you understand them and try to memorize them. All right, we're going to introduce two basic principles. Let me start with a simple example. I usually use that example. Suppose we wanted to fly from Boston to Shanghai. So you have a Boston here and Shanghai somewhere here. We used to have a direct flight. Now we don't have it for the moment. It's a pity, but let's assume there's a direct flight. It used to be here, Hainan Airline, so HA. And this is a direct flight. Or you could stop at San Francisco. Actually, you could stop somewhere else, but let's just make it simpler. You stop at San Francisco. Let's assume you have 3 routes you can choose from flying from Boston to San Francisco. Say United Airline, JetBlue, American Airline. And then from San Francisco to Shanghai, let's say you have only 2 routes. You can fly from San Francisco to Shanghai. So United Airline, American Airline. Now the question is how many different routes you can choose from if you wanted to fly from Boston to Shanghai. Okay, so many people to give the right answer is 1 plus 3 times 2, which is 7. Okay, that's the answer. This example shows 2 fundamental principles in counting. What I usually call them, very simple, but by simple way of saying is that if you have steps, you're going to multiply. And if you have different cases, you're going to add. Okay, so these are the basic rules. The first rule is called multiplication principle. And there's a theoretical rule. Let me introduce what that means. Suppose you have k steps to finish a task, and each step has say n1 ways to do the first step and 2 ways to do the second step and n sub k ways to do the k steps. And then totally you would have n1 times n2 times ... times n sub k ways to finish the whole task. So that's the multiplication principle. Okay, in essence, you have steps, you're going to multiply. A step is a non-completed task, right? While a case is a complete task. So for this flight route question, a direct flight from Boston to Shanghai by Hainan Airline is simply a finished task. So it is a case. And you have Boston, San Francisco, United Airline. That is also a different case. Okay, you have a 1 stop, and also this case, the second case has 6 of them, and within the second case, you have a multiplication principle applied. Okay, so keep in mind you have steps, you multiply, you have cases, you add. Now, when you have cases, you need to be very careful about double counts. We will have another principle called PIE, the principle of inclusion-exclusion. We're going to talk about that later on. It's a principle of inclusion-exclusion. Some textbook would simply call it inclusion-exclusion principle, but one of the textbooks says uses pi. It's kind of cute, so I adopt this method. this way of saying the principle of inclusion exclusion. Basically, you add, but then you have a double counts, you subtract those double counted ways. Okay, we're going to talk about that later on. But in general, you have cases you should add and be careful with double counts. All right, so let's look at some examples. A car plate number consists of 3 capital letters followed by 3 digits. How many possible plate numbers are there totally? We're going to do it by steps. Okay, so you have 6 things. The first 3 things are capital letters, and the last 3 are digits. So you ask yourself how many different ways to make the first position. Well, it's letter, capital letter. Alphabet, English alphabet has 26 letters, so there's 26 possibilities. And then the second one, we didn't say you cannot repeat the letter, so there are still 26 possibilities for the second position and 26 for the third. And you have 10 digits, right, from 0 to 9. And you have these 6 numbers. How are we going to deal with these 6 numbers? Do we add or do we multiply? We multiply because each one represents a step, not a case. So you don't add, you multiply. Okay. Another example. A committee of 3 members is selected from 100 people, with one serving as president, one as the vice president, and the other the secretary. How many such committees are there totally? We're talking about possible committees, okay? So again, we're gonna do step-by-step method. Okay, so first one, we're gonna select the president, and then you have the VP, and then you have the secretary. So how many ways to select the president? Well, you have 100 people, you have 100 ways. It's a common sense that you never select the same person to serve in a committee who occupies the 3 positions. So that's not a 3-member committee, right? So the next one, VP would have 99 choices, and the secretary would have 98 choices. And again, with 3 numbers, we multiply because in order to make a complete committee, you need to do 3 steps. You select president and vice president and the secretary. So steps, multiply. Okay, so that's another example. We actually have a notation for this product. We're going to denote it by P100 choose 3. This P is called permutation. So that's the notation of a permutation. All right. So generally, the permutation, the meaning of the permutation. So let's go to the next slide. So in counting P and K, permutation of n choose K, okay, is the number of ways of selecting K objects from n distinct objects with ordering. So order wouldn't matter. Okay, you select A, B, C versus B, A, C, they will be considered as 2 different outcomes or different selections. All right, so how can we figure out the formula? Well, you do this step by step, okay? So the first position, well, you're gonna select the first thing, right? You select kth object. So select first object. There are n ways to select the first object. And then you have n minus 1, okay? And then dot, dot, dot. Right, notice we have k of them. So the last number, the expression, what is that? We discussed that earlier. It's not n minus k, it's n minus k plus 1. You press 1, you subtract 1 and get 1 back, you get k, okay? So that's something, it's a little bit confusing, I guess. N minus k is actually plus 1. And then you would have a k minus 1. When you add 1, you get k. Okay, so that's the formula. And I want you to understand and sort of memorize the meaning of a permutation. All right. Let's work on some simple things. When k equals n, so you have p and n. So you follow the formula. So let's read the formula again. N minus k plus 1. So you start from n, then you have n minus 1, and and then last one you have n minus n plus 1, which is exactly 1. So I'm going to just put 1 here. We have a notation for that. I think many people know that. It is the n factorial. So p and n is n factorial. And related to the meaning of p and n, it's the number of ways of selecting n objects from n distinct objects with ordering. So it's simply the number of ways of ordering n objects, okay? Different objects. So in counting, I want you to relate n factorial with its meaning, the number of ways of ordering n distinct objects, okay? For example, you want to order n people, all right, then you have n factorial ways. All right, we're going to use this idea for the following problems. So you need to get used to the number of ways of ordering n distinct objects is n factorial. And vice versa. You see n factorial, you understand the meaning of that. Now, what is 0 factorial? 0 factorial is actually not 0, it's 1. There's several explanations, but I think one explanation, which is probably understandable and reasonable, is to consider n factorial as a kind of iterated way, recurrent way. So it's something like n factorial, right? N factorial equals n times n minus 1 times n minus 2 times ... and times 2 times 1. So it is simply n times n minus 1 factorial. So now you have a sort of an iterated way of defining n factorial. Now you plug in 1, so n equals 1, so you have 1 factorial. We know 1 factorial is 1, but then you have 1 times 0 factorial. That would make 0 factorial 1. There are a few very nice YouTube videos online explaining 0 factorial is 1. I think you could search for that. It's kind of fun to watch. All right. Let's work with a couple of problems, then I would introduce this concept of deordering, which is not standard. Not really. I didn't see any kind of textbooks. Maybe I'm not broad enough, but I didn't see any textbooks where they use deordering, but I use that to introduce no ordering thing, from ordering thing. Okay, so start with this problem. How many words are there if we randomly reshuffle letters in the word W-O-R-D? Here, words with quotation marks, it means it's just a string, so they may not have a English meaning, but we still count them as word. So for example, O-W-R-D, it would be a word, but it doesn't have an English meaning. Okay. All right. So how many words are there? We are ordering 4 letters, and these letters are all different. That is exactly n factorial. So you have 4 factorial for this problem. Okay. All the words, all the letters in the word W-O-R-D, they are different. So 4 factorial. Now, how about L-E-E, Lee? Well, the problem is that you have 2 E's which are the same. You change the order of these 2 E's, and the word doesn't change. It's still the same word. We can actually list all of them because there are only 3 letters, so it's pretty easy to order. So you have a L, E, E, you switch, change the position of L, you have E, L, E, and then you change the position of L again, you have E, E, L. That's all. Okay, so the answer is 3. But then we have more complicated problems like ha, ha, ha. You can still do it, but it gets more complicated. If you want to try ha 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 by listing all the possibilities, then what about Massachusetts? Now it takes some time to really find out how many different words there are if you shuffle the letters in Massachusetts. So we need to find a better way so we can generalize from simple case to more complicated cases. So the idea is the following. We're going to assume at the beginning that the letters are different. Then we order them, but some of the orders would mean the same result. So we're going to deorder them. So by that, I mean the following. So let's start let's look at this example of LEE. So at the beginning, I'm going to assign these two E's, consider them to be different. So I assign E1, E2, okay? And then we order them. It's 3 factorial, so 6 of them. It's pretty easy to order, so we can do that. Just list all the possibilities. Okay, so you do that. And you switch the order of these two E's. And then you have a E1, E2L, and switch the order of 2 E's. All right. So if E's are different, then you have these 6 possibilities. But then you realize, because if the 2 E's are the same, then these two are exactly the same. There's no difference. If E's are the same, then these two will be considered as one word, and similarly, these to be considered as one letter, one word, and these two would be considered as one letter as well. Sorry, one word as well. So now you see each order of 2 E's will be considered as only one outcome, one word, when 2 E's are the same. So you have a 6, which is 3 factorial, right? Divided by 2 factorial. This is what I call by deordering the 2 E's. At the beginning, you assume E's are the same. Sorry, at the beginning, you assume E's are different. Then you have a 3 factorial, but then they're the same. So you deorder them by dividing 6 by 2 factorial. So here it's very similar. You can really work out the chart like these, but it's a little bit tedious. I'm not going to do that. So we're going to just apply this method. At the beginning, assume all H's and A's are different. So we have 6 letters, assuming different. So you have a 6 factorial. But then you have 3 H's which are the same. So we're going to deorder these 3 H's. And then you have 3 A's. You're going to deorder them again. So you have 6 factorial over 3 factorial times 3 factorial. And then for Massachusetts, it's very easy. So you count how many letters are there totally. So we have 14 letters, right? 14 factorial. And then you divide by all the counts, the order, the number of ways of ordering those same letters, but assuming to be different, right? But you need to order them, deorder them. So you have 4 S's, you divide by 4 factorial, and then you have 2 A's, and you have 2 T's, and then you have 2 E's. Okay. All right, so 2 E's, 2 T's, 2 A's, 4 S's. All right. If you want, you can continue like 1A, 1M, 1C, but it's not necessarily, so we don't need to write that. This type of counting problems are called distinguishable permutation. All right. Distinguishable in the sense that these are distinguishable. So M or S is, okay, so they are different. But within each category, the objects are not distinguishable. Sometimes I just call them Massachusetts, Tallahassee, Mississippi type of problem, and people usually get it very quickly. All right. Okay, so that's this type of problem by using deordering kind of thinking. All right. And we're gonna generalize this type of idea to come up with another important concept in counting, which is combination. There are two concepts that are important: permutation and combination in counting. Permutation is probably less important because you can get permutation directly from multiplication principle. It's just multiplying things. Combination is probably more important. It's more widely used, and the specific topic in mathematics and combinatorics. So it's an important concept. So let's revisit we know the number of ways of ordering them is 6 factorial over 3 factorial times 3 factorial. And then we look at another problem. Say we toss a coin 10 times, how many outcomes have exactly 3 heads? So here, one outcome of 10 tosses would be something like HTHTH, HTHTT. So this is one outcome without any restriction. Okay, you toss coin 10 times, you get some outcomes like that. Now, outcomes with 3 heads are something like HHH, and you have 7 T's. So you have 3 H's and 7 T's. But the positions of H and T's can vary. So that makes it a little more complicated to deal with. We have a method, right? So let's see, can you see the connection between these two problems, so the ha problem and coin tossing problem? Oh, they're the same, essentially. You are ordering 2 types of things, 2 categories. And within each category set, there are some objects which are the same. Okay, so here you have 3 H's and 3 A's. And for this one, you have 3 H's and 7 T's. So using the idea from deordering, we would have a 10 factorial over 3 factorial times 7 factorial. Okay. We're gonna give a new notation for that. Let's call it C10 choose 3. Sometimes it's also commonly used is this kind of notation. Okay, 10 choose 3. Don't put this slash here. It's a notation, so it's not like dividing or anything. So similarly for 6 factorial over 3 factorial times 3 factorial would be C6 3, and also it is 6 to 3. This combination, this C means combination, and it's also called binomial coefficient. It has something to do with the binomial theorem, binomial expansion, or binomial formula. This bi literally means there are 2 things. You have HAs and HTs. If you have more than 2 things, then you would have a multinomial coefficient. And then you go back to this Massachusetts, Tallahassee, and that is actually multinomial coefficient. All right, you have more than 2 categories. All right, so this is a combination. I want to talk more about combination. All right. Let's look at this committee problem. Let's revisit the committee problem. So we're selecting 3 people from 100 people to form a committee. Now, what if the members have no rank difference? That means nobody is in the committees to be president. They are just the 3 members. They have the same voting power, no difference. Okay, so what kind of how many committees are there? Possible committees are there. So be careful. You have A, B, C, 3 people. So Adam, Bobby, and Caroline. So you have 3 people. And once they're selected, the committee is done. It doesn't matter who you select first, BAC, ABC, CAB, it doesn't matter. You have the same committee, okay? So, one way of looking at it is by using the idea of deordering. So at the beginning, you assume that there's a rank difference. Oh, we did that. Again, the rank difference, you have 100 times 99 times 98. But then the order of these 3 people doesn't make any difference in terms of the committee if there's no rank difference. So you're going to deorder them. Okay, the order of these 3 people wouldn't matter. So you deorder them by dividing this product by 3 factorial. Okay, so that's the answer for this problem if the members in the committee have no rank difference. We know that the numerator is permutation, so P100 choose 3, and then you divide by 3 factorial. So in general, this is true. Okay, the combination is permutation. So in general, the combination of C and K, that will be the same as P and K divided by K factorial. All right, so this is the one formula for combination. It's permutation divided by K factorial. And understanding K factorial is what? It's like deordering. It's the number of ways of ordering K people. All right. Let's work a little bit more about the formula. Similar to permutation, and in counting, and the meaning of C and K is the number of ways of selecting K objects from n distinct objects without ordering. Okay, so that's the meaning. I also want you to sort of understand it and memorize it. The sentence is a bit long. You need to sort of think through. So there are a bunch of formulas we can use. The first formula is the permutation divided by K factorial. Okay, that's we talked about it. One of the formulas. Let's expand the numerator. So you have n times n minus 1 times dot dot dot. What is the last one? It's n minus k plus 1. And then you divide by K factorial. Now, I'm going to multiply the numerator and the denominator by n minus k factorial. Well, you multiply by 1, so you're not changing any value. But now the numerator, what is the numerator? Okay, so if you multiply these terms n minus 1, n minus k plus 1, if you are to continue, the next one would be exactly n minus k. Then you have n minus k minus 1, and so forth. So the numerator now becomes n factorial. Okay, there's no gap, okay, in terms of the product, there's no gap. So it's n factorial. And then you have k factorial. And then you have n minus k factorial on the denominator. So that is another formula. That's another formula for combination. It is quite useful, at least theoretically. And also in the calculator, you're going to use this formula a lot. Well, some calculators have C and K directly, but some, if it doesn't have, then you can use factorial to find combination. Okay. Now we explained that the committee, if there's no rank difference, and there's a way of getting it from assuming there's a rank difference, then you divide, then you deorder, right? Now let's look at the problem with rank difference in a different angle. Okay, so I wanted to connect combination and permutation. In algebraically, it's pretty easy to understand, but I wanted to do it in counting way. So suppose we wanted to get a committee with 3 people, which has a rank difference. Okay, so we know that's 100 times 99 times 98, right, at the beginning with rank difference. Now we'll consider this task, right, getting the committee with 3 people with rank difference. This task, we're going to do it in 2 steps. The first step is to choose 3 people, just to choose 3 people, no order, just 3 people. So we have a C100, choose 3. Okay, but then you're going to assign each person a position. All right, so it's like you're ordering 3 people. So number of ways of ordering these 3 people, 3 factorial. And these 2 things are exactly the same. We are doing the same task, so these 2 values should be the same. It's basically just saying P and K equals C and K times K factorial, but kind of from counting argument. So I hope that you are able to get one from the other and back and forth. We'll be very familiar with the relation. All right. Okay. Let's look at the coin tossing problem again. We're going to look at the combination from a different angle. So at the beginning, you toss a coin 10 times and 3 heads, right? 3 heads and 10 tosses. You have a 10 factorial over 3 factorial times 7 factorial. We're using the Massachusetts and Tallahassee type of argument. At the beginning, you assume the letters are different, then you deorder them. This is exactly C10, choose 3. But then you look at the meaning of the counting. It's the number of ways of selecting K objects from N distinct objects without ordering. So where does this without ordering come from? Actually, we're ordering things, right? We're ordering 2 types of things, even though within each type, they have identical things, but we're ordering things. Oh, that's also, I want you to pay attention to this distinct objects in this expression here. All right, so let's make an argument from the meaning of C and K, which is the number of ways of selecting K objects from N distinct objects without ordering. So why these 2 things, the coin tossing, we will come up this formula from a Tallahassee type of argument, order, assuming different than deorder them. All right, so the argument, different argument for this is the following. So you toss coin 10 times. So literally you have 10 positions, okay? And then you're gonna, these positions are different, okay? And then you're gonna choose 3 positions and put H there, 3 heads, right? So for example, you put H here, you put H here, H here. So this gives you 1 outcome with 3 heads. But because the H's are the same, so the order of these 3 positions doesn't really matter. That's why you have C10, choose 3. Okay? So that's exactly the meaning of is that it's explained here. All right? So we have this combination, looking at the combination from two different angles, and they are actually, they mean the same thing. All right, they match, they're consistent with each other. Okay, so that's something about combination. Let's talk about some properties of combinations. There's some values. Let's talk about some values, special values. Let's do C. Let's do C. So C and N. So what is that? Well, you can use the formula. So it's n factorial over n factorial times n minus n factorial, but 0 factorial is 1, so it's just 1. Okay. So algebraically, it's pretty clear. But then I want you to try to understand it by using counting argument. So CNN, what does that mean? It means that you're going to select n people from n people and without ordering. So you select everybody. That's it. One way. Another one is C and 0. So using the formula again, you have n factorial over you have a 0 factorial times n minus 0 factorial. Again, it's 1. So it seems to be weird to think that, oh, there's one way of selecting nobody. Well, you consider this way. You select nobody. Suppose, say, you wanted to select somebody to do something, say, to do a work. Okay, so you select nobody to do work. It's like you're selecting everybody not to do the work. All right, so they're exactly the same. So CN0, CNN, they're both one way of selecting n people from n people without ordering. The same as the number of ways of selecting nobody from n people. I will go back to some other values later on, but the continuing this argument, I'm going to introduce an important identity, which is the following: C and choose K equals C and choose n minus K. All right. It's pretty easy to show by algebra, by the definition of combination and algebra. So C and K, that is n factorial over K factorial times n minus K factorial. And then C n minus K is n factorial over n minus K factorial times n minus K, which is exactly K factorial. So they're exactly the same. But I also want you to follow the argument I made earlier. So you wanted to choose K people from N people to do something. And then the left people, N minus K people, it's like you are selecting N minus K people not to do the thing. Okay, it's just a one-one relation. You have one way and you have the other way. They have you are doing the same thing literally. Okay, in terms of the counting, the number of ways are exactly the same. Using the argument in coin tossing, so you have 10 slots, and you choose 3 slots and plug in H. Okay, so say you have H, but that's exactly the same as you're selecting the other 7 slots and put T there. Okay, once you 3 are determined, these 3 positions are determined, the other 7 are determined, and the other 7 determined, and these 3 are determined. So you have a sort of one-one relation. Okay, so please try to understand this identity from counting. All right. let's work a little bit more about the values of some combinations, just to get some idea. When this C and K, when this K is pretty small, then you can use the permutation one. So this would be just 100. All right, and you have 100 choose 2. You can use a formula, but really there's one way of choosing. There's 100 ways of choosing one person from 100 people. This one, usually we calculate like that. 100 times 99, that's permutation divided by 2 factorial. And C 103, we can do similar things. You can do multiply, and then you divide by 3 factorial. Okay? Also, when k's get close to n, so for example, C 100 choose 99, then we use the identity. That's C 100 choose 1, and then you go back to this thing, okay? And similarly, you have C 100 choose 98, that is C 100 choose 2, and so forth. Yes. When k and n when k and n are either not close or not far away, or I mean when k is small, then normally we just use the formula n factorial over k factorial times n minus k factorial, because expanding them to write it is kind of tedious. Okay, so normally we just write like that. And the number is really big, so we usually don't ask you to work it out. All right. Okay, so in this class, I introduced 2 basic rules. I didn't talk much about the second rule, which is the cases case. We're going to talk about that later on. And then I introduced the permutation and combination. This kind of link between these two is when we deal with distinguishable permutation, and there are only 2 types of things, then the distinguishable permutation becomes combination. Okay? Combination is a very useful tool. So later on, you should be able to use the C and K to work with a bunch of problems. All right. Sometimes we don't ask you to calculate it out. You simply write C and K and then cooperate with other rules to come up with a counting solution. All right. That's for today. Thank you for watching. Bye-bye.